There's a nice little problem here that I do sometimes, just to kind of reinforce this idea of integration. How to integrate by choosing the correct type of differential mass element that mimics the geometry of the object that you're, trying to mimics the geometry of the object that you're, considering. So we can spend a little time on that. It's probably worth doing. Probably worth doing. Yeah, kind of got a little bit ahead in this course. So a little bit more time with some examples. Times I regulate those to problem solving sessions. Maybe I should do that with this. Maybe I should do that and keep moving along because I want to. That's probably what I should do. I was just going to do I mean, I did the basic kind of explanation of center of mass with discrete and then discrete systems of particles, and then we did the one with a continuous mass where I used the meter stick. And I just had some other examples that you might see, like I had a cone, a cylinder. I think I made that a cylindrical shape. With a cone, you can just do different shapes. It just helps to kind of practice with the whole integration thing. I think I might regulate that to doing it, maybe posting a lecture or something this week. I think I'll keep it moving. That's the best thing. Yeah. Here's where we stopped off. Yeah, so I guess that stopped off at momentum. So what my plan was to keep going. So I don't remember how far we've gotten with that, but I can read this really quickly. So the definition of linear momentum comes out of Newton's second law. I think I vaguely remember doing it, but let's just do it again, and then we'll go with conservation of momentum, and then put that together with conservation of energy. Somehow I feel like I could do that, but let's just do it again, and then that leads right into impulse. So then we can do collision problems. So let's start with Newton's second law as you know it. And again, I think I did this before, but it's always good to see it again. And we'll do it another time when we get to rotation. Just pretty quick since I think I did it before. A is dV/dt. Oh yeah, I definitely did this in class because I introduced thrust. But whatever, we'll just keep it going. Mass doesn't have to change. All right, but if it does change, it goes inside the integral. So we have time rate of change of mass times volume times velocity, excuse me. And yeah, and so I think I derived that out and showed you that you get two terms. One of them is thrust, one of them is just m times a. And if the mass is constant, the thrust term is zero. Uh, Excuse me. Yeah, and so yeah. Now we can then define the quantity in the term here, mass times velocity, as linear momentum. And with a symbol, we give it as small p, and it's equal to defined as the mass times the velocity of the particle, vector quantity. If you have a system of particles like we've been looking at, and the total momentum of the whole system, capital P, is equal to the summation I equals 1 to n of of the of the individual momenta. Yeah. And so then we can substitute 4 into 3, and we come up with a Newton's second law in terms of the change of momentum. And that makes sense if you think about it, right? So there's two versions, either these alternative versions of Newton's second law, but equivalent to the more popular, well-known F equals ma. So Newton's law can be stated that net force, external force on the system is equal to the mass times the acceleration of the system, or the net external force on the system is equal to the time rate of change in linear momentum. And again, I think I mentioned that equation 6 is more closely to how Isaac Newton stated the second law in his monumental work where he first introduced the equations of motion called the Principia. Principias for short, but I think it's Principia based physical. He wrote the thing in Latin, so I don't know, but it's basically the principles of the physical world or something like that. And in Latin, principles are Principia, plural. Always wanted to learn Latin. Maybe I'll try to do that one day. So, yeah, that's it. Now we can very easily move into. So, yeah, I wanted to point out that. So, if you have a car, right? Let's do this thought experiment here, where we have a car. It starts from the initial velocity of 0. Just going back to our kinematics. And when we first introduced Newton's laws, we said, okay, we've got a force. So if you start at position, x naught, and I'm going to accelerate to, to some other position over here, x. Let's say. All right, so that this distance is delta x, and maybe it's the engine of the car. I apply a force F, right? So we know that the velocity changes, and so if we know the mass of the car by the second law, we can determine that acceleration, right? Acceleration is that F over m, and then we use that acceleration in the equation of motion F equals v naught, which was 0, plus a times t, but that a is F over m times t. So that's going to give us the value of the velocity, over here at this point, v final, v of t. So I guess what I'm trying to say is that if I think about it in terms of momentum, at this point, the momentum is 0, right? This is P naught over here. P naught equals 0 because since momentum is mass times velocity, initial velocity is 0, initial momentum is 0. But over here, I could write this as, it has some final momentum at position x, because now it has a instantaneous velocity, v of t. So v of t times m is equal to the linear momentum. So the change in the linear momentum is basically, you see that it changes. So that's why these two statements are equivalent, right? Like F equals ma, or F equals the change in the momentum of the system. Now, what's nice is that when we look at conservation of momentum, basically, what happens when the momentum changes over a short period of time? For example, if I take a ball and I bounce the ball off of a wall. So I take it, this is the wall, take it, throw it on the wall. Right? So momentum is a vector. So it's going in one direction, and then it now is, after it hits the wall, it's coming back in the opposite direction. So I could look at the change in momentum over that collision. I could also look at it at half the collision. The ball goes into the wall, depresses a little bit, right? Deforms and then stops, then springs back off, as it relaxes that contortion or that deformation, and then comes back with the momentum in the opposite direction. We'll get to that more closely when we look at impulse problems in the next section. And be careful, because there's two minus signs there, right? There's the minus sign in the inherent minus sign in the delta quantity of delta p. Right? The change in momentum is inherently defined as final minus initial. So there's a minus sign there. But because momentum is a vector, one momentum changes direction. So you get two minus signs. And because it doesn't make sense, right? Like if I say where the momentum is going in is a certain value and it's the same. In an ideal case, let's say that you have a elastic collision or something where you assume that the energy is not lost. Well, then the velocity doesn't change and it bounces off with the same momentum that it entered. But if you just take the absolute value of the momenta of each individual, before and after the collision, then, momentum final minus momentum initial to the same value, they subtract, you get zero change in momentum. That doesn't make sense because clearly the momentum changed. I'm going in because it's a vector. Going in one direction, you have to consider that, not just the magnitude. And coming out. So there's two minus signs. Inherently minus sign associated with the delta quantity, but then because one momentum is opposite the other, it's minus a minus, so it's a plus, so you get double momentum, double the change in momentum, excuse me, which makes sense because, in an ideal case where you don't lose energy, that's exactly what's happening. But that whole process, you can use that to actually determine problems, determine, values of quantities without reverting to kinematics or Newton's laws. So it just gives you an opportunity to work problems in it's a separate theory, and ultimately it comes from momentum is conserved. There are certain conditions under which momentum doesn't change. That's an ideal case, so that wasn't really one of them. One I just gave. It's an ideal case if you assume that there's no energy loss. Again, ideal, which we do a lot of times with billiard balls and things like that. So as a first approximation, as a first problem type doing, we assume, or you could another way you can have that is like it's really nice that you can demonstrate in the lab if we're in class where you have an air track and you have cars on air tracks, but then you put magnets on the cars so that when they collide, they are not touching. So you actually hit a wall or something and it bounces back, but the magnetic force causes it to bounce without actually applying, a contact. And also it's sitting on an air track, so there's no friction or resistance there. So basically, that sets up a scenario uh, in which the momentum is conserved. And I think I stopped here. I think I'm remembering that. I think I asked you, what is the criteria such that um, the momentum of a system will not change between two periods or between two different positions? And the criteria is that the net external force must be zero. So if the net external force on the system is zero, the linear momentum of the system is conserved, meaning it does not change. Um, yeah, I do know we did cover this, but yeah. So if the net external force on the system is zero, the linear momentum of the system is unchanged or conserved. And so you can see from the equation over there that this guy goes to zero. We have zero is equal to p dt. But remember, in calculus, by definition, that's just the limit of, as delta t goes to zero, of delta p over delta t, right? So we're basically saying that delta p over delta t equals zero, and what must be true such that that statement is true? Well, delta t can't be zero for a couple of reasons. One, because if you are assuming that time is passing, changing, then, if you're not, well, I'll say it this way, if you're assuming that time is not changing, then it's a trivial problem, right? Nothing happens if time doesn't change. Nothing changes. But the other thing is that if that were zero, you'd be dividing by zero. So in order for that statement to really be true, what we say is that it's the numerator that must be zero, not the denominator. Not the denominator. So delta p is equal to zero. And that basically is a statement of conservation of linear momentum. It's one way to write it. Or you could say that P final, P final was P initial, getting the vector symbol. I could deal with the magnitude, or I could just, and well, actually, I was going to say P minus equals zero, and then finally P initial equals P final. All of these statements, equations 9 through 10, are valid equations for conservation of linear momentum. So it's the second of the conservation theorems that we've discussed. First is conservation of energy. And we always want to remember the criteria. It's one of my pet peeves or boxes that I'll stand on to remind you. Don't just use these laws indiscriminately. Know them, but also know the criteria for energy. Only conservative forces do work on the system. And for here, this is the criteria that the net external force of the system must be zero in order for linear momentum to be conserved. This becomes a huge criteria in central force motion and orbital motion in figuring out the equations of motion associated with satellites. And sending people to the moon and that sort of thing. So area of study that deals with that in central force motion, which is gravity, is centrally the highest located source of a center of mass of the massive body. It's a central force. Gravity points in radially toward the center of the mass distribution. That's what central force is. And so there's certain basic characteristics that's relevant for us to study that kind of motion. In conjunction with space travel and travel of satellites. And so when you have two systems, gravitational attraction on one another, both of those objects are part of the system. So even though they are forcing on one another, since they're both part of the system, those aren't considered external forces. Right? Yeah. So in that way, the momentum and the angular momentum, as it turns out, is conserved in both of those for orbital motion. And that's the other thing to point out is that when we talk about two objects colliding, sure, by the third law, one force is on the other force is on the first, but both of those cars are part of the system, so that's not considered external force. And in the case of our air tracks, right, when you have two cars sitting on air tracks, there are no external forces because Gravity is down, but the force of the air is pushing up, so that's balanced. It's hovering on the track. So in the y direction, the net force is zero, even though there are forces acting on you, the net force is zero in the y direction. And once you pop the thing and it's moving along, on the air track, it's moving along at a constant speed. Right? So there's no acceleration is zero, there's no net force on it in that direction. So when they collide, again, still no net force in the y or x. Y obviously because gravity is balanced by the air track, but in the x direction, even though one object forces on the other and vice versa, they're both part of the system. And by a third law, it's equal and opposite. So even when they're colliding, those things cancel out. And so you have a system where the momentum is changing, but there's no net external force causing that to happen. Unlike the way we normally think of, force and change in momentum. So it becomes a very specific class of problems that we will deal with here in the next couple of sections. But that's really, so if you want to figure out what those forces are, it's kind of difficult to inherently, you could go to Newton's laws and kind of work some things out, but you have to treat the forces, the cars separately and, define a coordinate system that's, maybe on the ground or, here it's just, we're kind of doing that anyway, but using conservation of momentum opens up possibilities that allow us to solve for kinematics, like basically what the velocities were before they collided, also what the value of that impulse force is. It is called an impulse force, a force that is the third law force on each object as they collide. And that's a class of problems called impulse problems. But it stems from really understanding how linear momentum is conserved, what linear momentum is, and this quick and dirty derivation, along with some of the explanations I give. And hopefully that makes it somewhat clear. And it may take a little while for you to read and sink in, but that's basically what conservation of momentum deals with at its most fundamental level. I do not know why I always start yawning after class. I'm not getting enough sleep on that. It always happens after I eat a little lunch. There's some disease or something. All right, so any questions about conservation of linear momentum from kind of a theoretical presentation or theoretical point of view as an introduction? So where do I go next in the notes? Oh yeah, a couple things. I think I said this already, but the units for momentum is you can see it from the equation here is kilogram meters per second. Maybe I didn't say that the other day. I think that's where I stopped. So units, kilogram times a meter per second. And it doesn't have a name, right? I'm just going to put P in parentheses as meaning it's the units for the momentum, but there's no specific name or anything we give to momentum. It's just kilogram meter per second. Just like we were saying the other day, this applies to a system of particles through this guy here. So all Newton's laws apply. The net force, the kinematics equations, they apply to kind of treat the different particles in the system as a moving body. Like I told you, like putting dots on a balloon, inflicting a balloon across campus, across the room. You could just find the center of mass and deal with that as long as you know the relative positions of the particles, the dots on the balloon, relative to the center of mass. Or if you just think of dots, in that shape of a balloon, or dot masses floating rigidly relative to one another. Yeah, if I could just go grand impulse. It's kind of nice. Yeah, I don't know. The great application for this is impulse. So maybe I should just jump on into that and we'll show some problems. All right, so that's conservation of linear momentum. Just jump on into impulse. And this example that I just gave a few minutes ago, this guy, that's an example of impulse, where you have a change in momentum over an extremely short period of time. Let me guide your intuition with that. You probably haven't thought about it, but like, for example, what was the length of the contact of that ball with the wall? Um, because that's the order of magnitude in which we handle impulse problems or apply impulse problems. A ball on the wall, bouncing a basketball on the floor, hitting a baseball, um, hitting a golf ball, you know, hitting a golf ball. Anything where you have a clapping hands, tennis ball, serving, or you're hitting a tennis ball, but anywhere bumper cars at the fair, anything where you have a collision over a short amount of time. But short has to be relative, right? So uh, something like those things. And what would be those? They're different, but like this situation where you have a hard ball and there's not much contraction of the wall or the ball, you hear from the sound, that sound, what was the sound, the length of that, will that sound last? I don't know. But if I'm counting like this, 101, 102, 103, watch, 104, 105, 106, 100. Yes, hard to. But, like I would say that would be less than a quarter of the time it took me to say 101. It was just a tap, right? So definitely less than a quarter. So that's 0.25 seconds, but probably even less than that, right? Probably might even say that it's, maybe a tenth of a quarter, so like 0.025 seconds, something like that. 0.05, 0.05 seconds, maybe half of a quarter of a second. Um, so these are just estimates, right? If it were something like bumper cars at the fair, I know you probably haven't thought about this, right? But I'm just asking you to think about it now, and I'm trying to give you some logical, sensible guidelines to think about it. If you're at a bumper car, right, like these little things, right, they're wide bumpers, and the bumpers displace, right? They deform when you bounce. So it's probably going to take more than 0.05 or more than 0.1 seconds to bounce. Definitely longer than this because it's got to deform. Like if this were a ball, right, and it's hitting a wall, like if it were a spongy ball in a slow motion camera, what you would see is something like this, right? It starts to deform, presses in, goes flat, then bounces back, loses some energy in non-ideal case, and comes off. In an ideal case, it's completely inelastic where it bounces off and comes back with the same velocity that it hit or speed that it hit the wall. That never happens ideally, obviously, because friction causes some of that kinetic energy to be converted to heat. Also, the sound that has to have energy. So all that energy came from the kinetic energy of the ball, right? And so when it bounces off, it can't possibly be the same energy because some was lost to creating sound, some was lost to generating heat, um, both in the friction of the wall, but also the internal friction of the ball on its own atoms as it deformed, right? You've seen that you take a wire, wind it up, it gets hot. Take a ball and press it, it's a certain constitution for it to get warm. So that energy is heat being converted from mechanical energy. So that never happens. There's never actually. So when you see that in your book, keep in mind that these are ideal cases, kind of like frictionless surfaces where something can bounce off. But again, I digress a little bit, but we'll get into that. We'll get into collisions here in the next section. Right now, we're doing impulse, and I'm just trying to describe qualitatively and guide your intuition for problems in which, actually, which these are most ideal. Actually, this physics applies even when problems are not very large, even when the time is very large, right? Because it just comes out of Newton's second law, and Newton's second law always applies. But the reason that we do it here, and this is a crucial point, whenever I'm doing like this example that I gave here, and pretty much all throughout this class, and I told you this on the first day or the first week at least, we generally assume constant acceleration. We kind of know how to handle it, even if it's not. We just integrate it, we differentiate, right? If the acceleration is changing. But, we don't want to become overly mathematical, and we do that kind of stuff at a junior, senior level physics class. But at a sophomore, junior level class, we just do a constant acceleration for the most part. However, there are a class of problems where we have a way of dealing with it, where we basically take shortcuts. And if you think about it, this is one of them. Because in all of those examples that I gave, the basketball, this guy on the wall, the tennis ball, the golf ball, you're going to have deformation of the ball when you hit. Like you've seen those time lapse casts. You look at a basketball bouncing or someone hitting a golf ball, and the thing is completely deformed in that instant that's in contact. It's like looks like it's even the same ball. It looks like it would break apart or something. You've seen those pictures of that kind of thing. Commercials show that kind of stuff as well. I think I've seen a couple commercials over the past couple of years where they show that. Probably do it really well now with any basic eye camera if it's not too fast. Velocities and momentum changes are not too fast. You can probably what they did it with. In fact, man, that might have been what I saw it with. In one of those commercials for your iPhone where they were doing really nice pictures and showing the resolution of the thing. That's one thing you could do. But if you, I should try to set up something like that. Anyway, if you think about it, a rubber ball abides by the same similar physics to a rubber band, meaning it stretches. So if you were to look at the force that it applies to something or the reaction force that it has as you press it, what you would see is that the reaction force that it delivers to your hand as you try to press it is is proportional to how far you press it. The more you press it, the larger the force. Or like with a rubber band, the more you stretch it, the more the restoring force it applies on your hand. As long as you don't go past the critical limit that could deform the system to the point where its uh, uh, critical limit has been violated and it will not take the original shape that it had prior to the stretching. As long as you don't go past the critical limit, it will bounce back. And so under those circumstances, is when Hooke's law applies. And that is the name of the law. Remember, Hooke's law defines the force of the elastic force of a string, but it also is loosely applied to any kind of ball you could have, any kind of basketball, football, tennis ball, whatever, football, right? If they compress, it also abides by that law. It's a linear relationship between the reaction force and the deformation of the ball because you're taking it beyond its equilibrium point as you come back over here. Yeah, so So we have Hooke's law, right? We have um, is that F is equal to negative K delta X. We talked about that. Has a potential energy associated with it, but I won't talk about that just yet. We don't need that. Just want to remind you of that law. So if you look at, in fact, let's do this. Let's do a thought experiment. I did that. I took the ball and threw it against the wall 2 or 3 times. Let's see if we can break that down and look at it kind of from our own. Let's do a thought experiment where we're visualizing this process that I just showed you, where the ball hits, deforms, and bounces off. Let's try to visualize that and do a thought experiment where we think about what's happening in terms of the momentum at every point. Um, and let's see if we can say something qualitatively about the reaction force that the ball has on that the wall has on the ball. Because remember, by the third law, when that ball hits that wall, right, it starts to depress, squeeze it in. While it's doing that, the ball is applying a force on the wall that basically increases as the ball deforms, right? Because of the delta X is changing. But here's the wall, and the force of the ball is on the wall, right? Like that. I don't know, like whatever. But yeah, maybe I should do it like that's the wall. Those people do that. I can't do that. I can never do that. But the ball, by Newton's third law, the wall, excuse me, by Newton's third law, as that's happening, is a force on the ball that's increasing. Well, you tell me. That's the point I'm trying to make. There's a reaction force on the ball. And it's that force that causes the ball now to accelerate off. So you can think of it like that, right? Or and try to figure out that force and then figure out the acceleration and using it. But it's a difficult problem, much more deceiving than you realize. And I'm going to show, and I'll prove that why. So we don't handle it by looking at the force, at least not explicitly looking at the force. We handle it by looking at the change in momentum. And let me show you why before we even start. So I'm going to go through and I'm going to set this problem up and do 6 or 7 steps and walk you through qualitatively what's happening. Right? And then I'm going to ask you to do something um, in terms of graphing the force versus the displacement of the ball. I know it's small, I'm making it exaggerated, but even with this thing, if you throw it, the deformation is so small that you probably couldn't even see it very well. But clearly it's deforming, otherwise the ball would stick to the wall, right? It's deforming in such a way that there is some sort of force that is popping it back out, right? Which we could think of, as I said, in terms of a force or in terms of change in momentum. It's a couple of different perspectives. But let's do this thought experiment right now. Now, so 1, 2, 3, 4. So I'm gonna do 4 steps, ball going toward the wall, and then 4 steps, ball bouncing off the wall. A little bit tedious, kind of overkill maybe to do, but I always find this works really well. So it's worth the time for me to draw all of this out and kind of do a thought experiment where we have a proposed time lapse camera looking at the ball as it progresses toward the wall and is and bounces off over here. Okay. All right. I don't think we need this anymore. Just wanted to reiterate that it's the elastic force we're dealing with. Now, the ball in this case, it's moving toward the wall at a certain velocity v. I think I numbered these. So v1, and the reaction force in this case is there's no reaction force because we're not hitting the wall yet. So F1 equals 0. Now, here, the ball is just touching the wall. And so F2, yeah, so it's non-zero. And now again, it's the reaction force that we're going to dictate. So the ball touches the wall, begins to compress because of Hooke's law applies a force on the wall, and the wall applies an equal and opposite force on the ball because of that. So I'll just maybe draw it like that. So that's F2. Okay. Now, as the ball compresses, delta X increases. So that times the kind of elastic coefficient of the ball causes the force that it applies. Now, I'm not going to show that force, but there's a force on the wall. Maybe I should. I don't know. Yeah, sure. Why not? So there's a force on the wall, and it's also equal in magnitude to F2, right? Now here, that force gets larger. Why? Because, well, it's, Fx gets larger. I've never drawn F. Yeah. So here, that F2, back then, it's F3 now, right? And then same thing here. Now the ball is compressed fully. It's mattered like a little pancake or something. I know. But definitely splattered on the wall. And so there's a maximum force at that point of the wall on the ball back in this direction. Maybe something like that. So this is F4. Okay. Now it just backs out, right? Now the thing, it stops and it stopped compressing. Now it's coming back in the opposite direction. So that starts the process. I'm just gonna, and yeah, I didn't say anything about the velocity. So the whole way, the velocity is, well, technically speaking, once the thing hits the wall, the velocity is 0. But I don't know, like not all the particles have completely stopped. Yeah, I think I probably would. Probably not necessarily to put the velocity, like it had some initial velocity before it touched the wall. So I want to, because they're all, the average velocity at all these are 0, right? Because it's on the wall, it's not going anywhere. So, but then now I'm reversing the process and I'm coming back off the wall. So the tendency of motion is in the opposite direction, we could say. But here we still have the F4 at this point, pretty large force. And then here, the F2, so it's F3 that is. Right, it's starting to decrease because we're popping off. So, and again, in an ideal case, this is not ideal, so I'm drawing an ideal. Well, I didn't really fix. I'm not putting any numbers in. I'm not saying how much the velocity is, but yeah. So if F3, no, sorry. Yeah, backing out. So F3, F4. Over here, same thing. We're just about to come off the wall. And we're back to F2 again. And then once we leave the wall, our velocity is completely reverse directions. And we can think about a change in momentum. So V basically 1, now the magnitude is back in the opposite direction. And there is no force. There is no force on the F1. Again, it's back to 0. So what I want you to do, I've tried to help you by, making the size of these vectors associated with the reaction force, different lengths. I didn't do that. But what I would like for you to do is to go ahead and calculate, and not calculate, but to sketch what a graph of the first half of the step would look like, process, and then connect it, basically the overall process. But think about it in steps. First this step, and then finish it out with this. And what you're graphing is going to be the value, the qualitative value of the force relative to the displacement of the ball, the delta x of the ball. So basically, and we can make it like this. Let's say that the total ball was displaced through a delta x. That's this distance here. So this total distance here, I mean, I guess the way you could do it is that this is the maximum, x max, right? And so half of x max is here. And let's say that the maximum force, F, is here. So F max, or F4, let's say. Now, I know that I've kind of broken this down into 3 steps, but, like just assume it's continuous, right? You could have put an infinite number of dt's in here and got an infinite. So, you don't have to about 4 things. It's like, what would the continuous curve look like if you could see the force, the reaction force increasing to its maximum at F4 and then decreasing back to 0 from this position, I guess would be 8 back to, or 5 back to 7, position 5. And so let's make this the maximum qualitative value of that force here. And so what does the curve look like here? What would you just guess? And I know we haven't quantified it anyway, but I just want you to guess. Yeah, see if you could draw, and because we only have a couple functions, right? We got linear functions, we got exponentials, we got power functions, quadratics, and something else. What else? In 2 dimensions, we have linear, quadratic, power functions in general. I guess logarithmic and then exponential. Or exponential then logarithmic. So, but this curve is a classic curve. It's kind of honestly, it's kind of a combination of a couple of those things. In different places, but it's a curve that's basically, it's a huge symmetry. That's what I'm getting at with other types of systems. In fact, things that you probably wouldn't even relate it to. Back in the 80s, let me just talk about this for a minute. It's something that kind of the precursor for some of the things I talk about in thermodynamics, or at least in the one of the topics in Physics 39 associated with thermodynamics, which is the kinetic theory of matter. I'm going back to this, looking at how energy is transferred with this Einstein model thing in the 4x law, the whole springs. But this is just a great symmetry. Everything, we've talked about this before, right? Everything is energy. We've talked about, at least qualitatively, I've tried to describe it. Even at the beginning of this conversation with mechanical energy, I gave you this big spiel and 15-minute lecture about kind of broadening your sensibility with respect to the quantum level, and everything is built up from there. I also talked about the fact that on every level, order of magnitude, things repeat themselves. So these are kind of fundamental kind of precepts that I want you to just kind of begin to have in the back of your mind and develop in just a general way of looking at the universe. That said, this curve that I'm alluding to here, the reason that it applies to a lot of different things seemingly unrelated is because of ultimately, you can think of it in terms of energy. One of the places that they use this curve I'm talking about is with these well, I don't know what they're doing about it now, but back when I was probably in my 20s and 30s, it always comes back, like every 10, 15 years it comes back. And this network marketing, this some people call it a scam with the pyramid thing, but it's actually not a scam. It's actually a valid business model. And I think it's called, well, what we used to call it, or what it was called when I was, younger, was network marketing, where like it started with Avon, and I think even the business models that they use are like McDonald's, Henry Crock, or whoever his name was that started McDonald's. Someone had started, and then this Crock guy came along and basically started, got somehow rights to the business and started making McDonald's based on this network marketing thing where, you know, you sell the product, but you also, the business itself is the product. So in order to expand, you go to someone, you say, well, I got McDonald's, I want to sell some hamburgers. You can come work for me, but if you have enough money, I can sell you a part of the franchise, your own one, and then you can go out and find other people to uh, to run the McDonald's. But if I sell you this name McDonald's, you have to run it the way I say, based on our company policies, and you have to give me a cut because you're using my name to sell those hamburgers. And McDonald's was one of the first, you know, chains that actually became hugely successful. And obviously, it's still around, and it's still set up that way, right? So the model, I think, was initially started by, it was either started by the McDonald's or it was started by Avon, and then Avon. I think, I can't remember. I think maybe, but very shortly after McDonald's started, Avon copied that because they used to sell, like cosmetics door to door back in the day. Even when I was a kid, people in the early '60s, the late '60s and early '70s, people were still doing that. Um, but then at some point, Avon adopted this business model where you go to someone's house and you're not just trying to sell them perfume and get a customer, you're trying to get them to be in this business where they're now selling perfume as well. And Avon saved itself doing that. Then scroll forward 20 years when I'm in graduate school in my 20s, and we started to have technology and stuff like cell phones come out. People took this model and just went, you know, crazy with it, and just started doing it with everything they could think of. And they would go to college campuses and try to recruit people to do stuff. Like it could be anything. Someone comes up with a new cell phone and they come in, so they get a bunch of people to go out and try to, sell network marketing. And the thing is, it kind of works. I mean, it does work. Like anything, like uh, one of the big things that was it was workout equipment or protein shakes. Like we didn't have Amazon back then, right? So, and Amazon has kind of killed it. It's still around, but it's not as prevalent as it used to be. At least I don't think it is. Maybe I'm just not in circles where I see it. But before the internet, before Amazon, it was big, and it was all over the place, and people made fortunes on it. Some people did, but a whole lot of people lost money on it too. Went broke because it takes a lot of energy to do all that. Anyway, I'm bringing that up because when I was probably in my late 20s, early 20s in graduate school, and was not quite graduated yet and running out of money, some people came to me, right? I didn't know anything about it, and they approached me, and so I went to a couple of meetings. And one of the things that they tell you is that they break this, like I say, if you want to sell protein shakes, I don't know, some sort of protein powder. So you come to a place like I was at a big university. I was in Raleigh, like I was in my master's degree at the time. So it's with the Wolfpack. So there's like ACC basketball, like I was at North Carolina State, but we were right near UNC, Duke. It's all in that area, right? Um, and so one of the things that was big was like athletic type stuff and like protein shakes, something like that. That's one I just happen to remember. So they break the whole area up into certain regions, and they say, okay, well, when you we're starting in this region now, and it's fresh, right? So it's a good time to get in, right? Because not only is it not the region not saturated, because at some point it'll be saturated, and it will be all sold out, so there will be no new customers to sell. Right? And remember, the key really isn't the product because that's going to also resell. The key to make big money is getting people to sell it for you, and then they give you a cut as you go up the chain, so to speak. But that's only going to last a certain amount of time. And so what they showed you this graph, it had a specific type of curve on it, and they would say, okay, you need to get in right here at this part of the curve, because when we get to here, the linear portion, or a little bit here, it's going to start to be saturated. But right now, you get in before it gets to that critical point and things take off. If you're at that point, you're basically at the, in my words, not the words they would use, but you're at the top of the pyramid. And pyramid, it's kind of a negative, because pyramid scheme does have negative connotation. And that's something that's used, Wall Street with the whole Bernie Madoff thing. But this is pyramidal, or whatever, if that's a word, but it's not quite the same as that thing. And it actually is, it's a legitimate business model. Like I ended up never doing it because it just takes so much time, and that's what they don't tell you. Like, you have to fully commit with that thing. And I was, I was in graduate school. I was trying to get my degree in physics. I didn't really have time to do all that. And I don't really have a sense of it. I don't really want to do that. But for people who are really motivated, it actually works. At some point, I realized that this whole model thing they have is actually based on physics. It's based on thermodynamics and statistical mechanics. And that's what that curve is. And they're right about that, because it's not only that, if you think of the people in a certain area as the possibility of taking this, think about it like energy, right? Like, if you, that maybe is a good term, because you have to got to be very energetic to go out. And that's why those meetings are always like that. You go to any of those meetings, if any of you know what I'm talking about, and it's, they get these really energetic people, and they're getting you hyped up, and you could sell all this stuff in a certain amount of time and make all this money. And so, like, people get energetic, right? And they go out, and part of what you're selling is that energy, that personal charisma to get people to try it. It's a really great analogy to what's happening in a lot of systems in physics. And so, if you think of it like they infuse that energy, they start to vibrate, right? But if there's a certain amount of people, there's only a certain amount of people in a particular region, there's only so much energy that can be received by those people. And if you think of it like that, it makes sense why this curve is the shape that it is, and why it repeats itself in so many different scenarios that seemingly are completely unrelated. Like, I'm talking about the force on a ball, and why am I talking about selling, Avon in a pyramid scheme? It's symmetry. Remember, symmetry is a theme for the course. And because the curve is the same reason, because the relationship of those variables and parameters in that business model, based on, the customers and people that they're selling to, is similar to, basically, here it's the molecules of atoms in this ball that is depressing. Another place where it applies is when you're warming up something in a conventional stove, right? It doesn't warm up automatically. The outside warms before the inside. But if you were to look at the rate at which the whole thing warmed per unit distance, it's going to be the same curve. Because on the outside of the cupcake, let's say, it's getting heat from the molecules of air hitting it, right? Molecules of air hit it. But now those molecules in the atom, think of the Einstein model, they start to vibrate. And also, but now it's not just that the molecules on the inside of the cake that are not warm, that need to be warmed. They're now going to be getting, you know, whereas the surface of the cake, it only has molecules hitting it, I guess, from the surface, so to speak. Like, no matter, if you have a steady rate of heat hitting the surface, once that rate is hitting the surface, it's very difficult for me. I guess the rate at which those molecules take on the energy is going to be a constant. But if you look inside the material, and kind of, even if you think of it as two-dimensional, as the energy is moving toward the inner part of the material, um, well, I guess it kind of defeats it. It really doesn't heat like that, right? That's a simplification, because the heat is going to be coming from the top, it's going to be coming from the side, it's going to be from the other side. So now the molecules are going to be heat faster relative for a particular displacement of for a particular displacement. If you're thinking about like heat per unit length within the material, because their molecules, the heat is coming from several different places, right? From the top, from the different sides. And so that causes the molecules that are not being heated to be privy to more, I guess, heat surfaces or heat waves that are incident on the places that are not being heated, as opposed to just thinking of maybe the sides or the tops, the outer portion of the material that's exposed to the external heat source of heat. So that you can say with many things, right? It's why something doesn't heat up at a linear or a constant rate. It's the same reason that water, like how they say water heats faster if it's already warm. It's the same reason. And what they're not saying there that if you start with cold water and if you start with hot water, the cold water is going to boil faster. That's not what it means. What it means is that if you look at the rate at which the water takes on heat, hot water takes on heat faster than cold water. It's counterintuitive, right? You would think it's the other way around, but it isn't. If you actually measured the amount of energy that's being absorbed per unit time, I'm sorry, that just screwed that up. Yeah, I did. I have it backwards. My bad. The cold water actually, sorry, I was a dyslexic moment. The cold water actually takes on heat faster than the hot water, but it's never going to catch up and pass, the hot water, right? Because that's illogical. But uh, if you look at the amount of heat it's taking on, if it's cold, in those colder temperatures, its heat changes. It takes on heat faster than water that's already close to boiling or hot. And it's for the same reason that I just mentioned. You just have to think about it. But I mean, that's the best I guess I can explain it, without spending more time or having some sort of demonstration where we kind of show maybe some measurement devices. Like that would be a great example to show. Have cold water and hot water, and then maybe have a graphical display where we show the amount of heat. But that's something we'll do for different. But I guess what I'm trying to say is that those are really good examples, but they're kind of out of the scope of this course. But this idea of taking on energy is a symmetry with examples and correlations of systems that are seemingly unrelated because it's a fundamental way in which our objects or in which systems within our environment interact with external sources of influence, whether they be heat or, in this case, force, what have you. So, after saying all of that, does anyone know what this curve looks like? Could you draw it? In fact, let's do first, like the first half. What would it look like going from uh, the ball with no contact to being fully compressed? What would that curve look like? Where the zero is here at the origin and the maximum force would be at that point right there. And this would be the value of the force. And if you have, yeah. So what do you think it would look like? Um, Esperanza, are you there? And it probably is in your book as well, too. I'm sure they do some discussion about this. Who's in class right now? Kareem, are you there?
Can you ask the question one more time?
Yeah, Armand, how you doing? So this is a plot. I'm plotting. This is like f of x versus x. This is x, right? So if I were to look at this reaction force, and you were to give a plot, a graph of what the force looks like, what the functional form of the force looks like, as the ball is compressed against the wall during the course of this collision, what would that function look like? Would it be linear, be exponential, be parabolic between this point and that point? How does the force, we know it increases because we see that the ball is, and I kind of said that it was Hooke's law. I did say that, but delta x. So you might be tempted to say linear, but I guess I might have misled you because it is actually a Hooke's law, but it's complicated. The Hooke's law that we did was an ideal Hooke's law where there was no mass associated with the object. So it was like a frictionless surface type of situation. But if you've ever tried to compress a ball, you know that it isn't completely linear, right? Well, you might feel that. It's hard. Well, I don't know. I guess what I'm trying to get at is, how do you think the resistance of the ball, because that's really what we're talking about, changes as this ball is compressed during its collision? And can you sketch a graph that indicates at least an approximation for what that force looks like between position 1 and position 4? So I don't know. That was very convoluted. Does that answer your question, Armand? Do you understand what I'm asking?
I think so. Is that the graph for an external force?
Yeah, well, it would be external, I guess, if you assume that the wall is external to the ball and the wall is applying the force on the ball. So yeah, and that's the force that I drew up there, that blue force. So yeah, it's an external force and it's the reaction force of the wall on the ball. That's right. What would it look like here?
Like a parabola?
A parabola. Well, okay. Let's go with that. I agree that it would start off like that in some way, right? But here's what a parabola does. Parabola the force just gets, larger and larger, right? Is that what that force does?
No, isn't a parabola like a sinusoidal curve up and down?
No, a parabola. This is a parabola, right? Parabolic? No, this is a parabola. Sinusoidal is something different, right? Sinusoidal is, but good. You're thinking the way I want you to think. Yeah. All the different functional forms of what we talk. Sinusoidal is something like this. So you said kind of two different things. You said two things, but those are two separate things. That's
I meant
parabolic.
sinusoidal.
Okay. Okay. Well, that's better. Sinusoidal is something like something like this, right?
Right.
Okay. Okay. Yeah. And so that's actually a little bit better. So I'm assuming you mean something like that. Is that what you mean?
Well, what is that point where the f of x crosses? What is the dash lines? What are the two dash lines for?
So this is just the halfway mark. Because right, it compresses, then it bounces off. So yeah, sorry about that. So this halfway mark is just between this point. And this is the maximum force that would have at that point when it's fully compressed.
Okay, then that's what I thought it would look like.
Okay, well that's cool. That's cool. I would agree. I would agree. I turns out it's not actually. And this is a fine point. It's not quite sinusoidal, which is a specific type of function. It's more of a what we call an S curve. But I'm kind of I'd ask you to do it qualitatively, and you're right. So it would look more like an S curve. An S curve doesn't quite have the same type of function. It's going to be something more like that, which is not quite sinusoidal. You can see I've drawn the difference there. Hopefully you can kind of see it. It's not quite the same as what a sinusoidal would be. A sinusoidal is more like what I drew before, but the differences would be something like that, right? So it's not quite sinusoidal, but good. But your intuition was dead on, and that's exactly what I wanted. And so basically, it does kind of what's called an S curve, and this is the curve that I was alluding to, and all those things that they would draw. Like they would kind of blow it out. They wouldn't, because here we're kind of coming back off. But what they would do in those, if any of you have ever been to those meetings, I just want to, any of those like network marketing things. In fact, S curve was a big deal with those things. They would always get in all this kind of, so they would give you something like this, and so they would give you like a saturation point of when the market would be saturated, and they would say, well, like you start off down here, there's not going to be a whole lot of people selling, and you're going to sell faster, right? And then, but at some point, it's going to be saturated. It's going to get close to saturation point. So they'd say like, well, you want to get down in here before this point, because at this point, because that's a linear portion of the function in there, right there. And that's a characteristic of this type of function. And so when it gets in that linear function, that's the highest rate at which it's uh, basically you can sell stuff or that the change is happening. And so that's the same thing in here. There's a linear part of that function or an S curve right in here, right in there somewhere. I don't know. And you get in down here someplace, then you can make a lot of money. Anyway, they would just talk about all it. But the interesting thing is, I realized when I got to some more advanced fit is that that's what this is. And so what it's showing you is that the force is not constant. The force definitely is not constant, right? Because that's what a constant force looks like. And so in order to use Newton's laws, you actually would have to know what the functional form of that force is in order to get the acceleration correct. And because what it's telling you is that, and once you think about it, you realize, okay, well, that's true. Like this ball, the acceleration is clearly not constant. So that force clearly is not constant. But the thing is, it's dependent on a bunch of stuff that it would be almost impossible unless you have some supercomputer to actually figure out the correct functional form. Because it turns out that that force is dependent on a lot of things that are not inherently associated with the ball. It depends on the temperature, in the environment. It depends on, like probably the material of the thing, I don't know, like it's probably more geometric than anything else. I usually things do depend on geometric process, right? So probably that's what it would depend. But definitely it's dependent on the constant associated with the ball, the constant of the ball, and the constant associated with the thing that's hitting the ball. And a lot of times those things are dependent upon the geometry of the objects. So, but then, temperature, humidity, all these things matter in terms of the response of a ball, right? So that's all the stuff that you would have to know in order to fully know what the functional form of the ball is and of the force is, and therefore the acceleration. But one of the things that we do is we realize that this is a specific type of curve. Two halves of an S curve is what it's called, is actually a curve that looks like this. And this curve is something called a Gaussian distribution. And so from statistical mechanics, there's a very nice way that we can deal with Gaussian distributions. Now, we're not going to get into statistical mechanics here. I'm just saying that this idea of how we handle impulse and the equation that I have, it comes out of, the equation I'm going to give you here, it comes out of statistical mechanics, actually. Well, you can derive it with Newton's second law, but it's some kind of thing that's used in, um, getting average values of quantities over a particular time is the kind of thing that's done in some more advanced higher level physics. So this is a Gaussian distribution. And what for Gaussians, what we say is that the average value of this force, F average, turns out the F average is a constant value, right? It's on the graph, it will be like a constant essentially, right? The graph of a constant value is a straight line. So for Gaussian, it would be someplace about right here. And it turns out, remember, this is a situation where uh, the area under the curve, I think I screwed up. But that be X or time? That should be, sorry, this should be time, not X. It's time. Oh, wait, is that so my notes? Yeah, it's time. My bad. So I want to look at how the force changes in time, not in terms of X. But still, my argument is all the stuff that I said is true. It's changing like this because of the molecules and how they're taking on the force the energy as it compresses. Anyway, um, this is another case where the area under the curve has a specific meaning, and the area under this curve is going to have units of, well, if you look at the area, it's in order to calculate the area of the Gaussian, you would have to know the functional form of ft, which we don't know. But if you assume the average value, and it turns out that the area of this curve, of this rectangular shape, is very close to the approximation of the actual area under the Gaussian. And so what we do is it's close to this area, right? So what we do is we say, well, we could just deal with this guy and take the average value of the force of the Gaussian as opposed to dealing with the Gaussian. And it turns out that the units of F times T is a Newton second. And it turns out that will have, if we break it down, let's actually break it down right here and do a unit analysis. So a Newton times a second, that's going to be a kilogram meter per second squared times a second. And how about that? That's going to be, so seconds cancel, end up getting kilogram meter per second. If you look back over here, well, I've erased it already, that's units of momentum. It's momentum. So basically, the area under the f of t curve is the change in momentum of the system as that ball compresses and bounces off. And so from that, we can basically write down an equation and also define it as an impulse equation. In fact, we define the change in momentum of a system, particularly if it happens over a short period of time. Technically, it's any time. It's always the case. It always applies, whether it's a collision happening over a long period of time or whether it's a collision happening over a short period of time. But over a long period of time, we generally have other means of working the problem because we can figure out the acceleration, right? We can figure out the function of form. It's not happening over a short period of time. The thing here is that it happens over a relatively short period of time. So there might not be an ability or a way to figure out what that functional form is. But you also always can easily determine the momentum before and after because you can look at the velocity before and after. And so you can use that to backtrack to actually figure out what the average force is very quickly. And even though that's not the explicit force, F of t, it's very, very close. Usually for problems where the time is small, like hitting a baseball or hitting a tennis ball, the amount of error in the difference between the average force and the instantaneous force at any particular time is so small that it basically doesn't matter. Yeah. Oh, sorry, I didn't see you respond there, Cleve. Yeah. So that's the deal with impulse. I think I went over the break too. What's that breakdown? Oh, it's right now, 2:30. Yeah, great timing. So I'm going to write that down, and then we'll come back and we'll start to investigate some problems with impulse, showing you how to use that to figure out some stuff. But yeah, so I'll just basically just write that down, right? The area under. So there's couple of things out of this that I want to want to take away from this. One is that this is the third time I think we're seeing where the area under the curve has meaning. The first time was with the velocity equation, velocity versus time. The second one was with work and energy, that force per distance, force over distance was equal to work. And now this is force over time, and that's equal to impulse or change in momentum. And that's essentially what impulse is. It's change in the momentum of the system. Let me get some more ink. Be right back. Yeah, so what am I doing? Oh yeah. So uh, here we can say that the area under the f of t versus t curve is the change in momentum of the system during that time period. And and change in momentum. That's a change in momentum. I should put well, the time period is delta t. Let's put some parameters here. The change in momentum is delta p. Change in momentum of the and so we can say that impulse and I, it's the symbol, is equal defined as the change in momentum. The change in momentum. Well, I'm gonna use J. Sure. Well, whatever. Some people use J, some people use I. Um, Somehow I got J in my notes, so I'm gonna use J. I don't know what your book uses. And so that defines the change in momentum. That's actually one equation. That impulse is defined as the change in momentum. So is impulse J is defined that impulse is what? I think I'm hungry. Sorry. Impulse J is defined as change in momentum. Change in momentum. So J equals delta P. So we have, yeah, okay. Now, when we put those two things together, so the area and the curve, if we're taking the average value of f, then, area, we did that problem, something like that before, that's just length times width, right? The actual area. But the length is the value here, the average force, or the height, I guess, and the width is delta t, the time period and that time. So if we come over here, we can say that, the change in momentum, because we saw that from doing a unit analysis, that's what it is. So delta P, how much is the momentum change? Is actually F average times delta T. So we could put these two now, I guess I'm going to do something here a little bit. I could take the limit, right? I could take the limit, like, it basically, I could say that average force is equal to delta P over delta T, which I can do that because, it's an average force. So that's really what it's implying, is that, uh, whereas the force really does change because the force is changing for the average force, the overall change is a constant. So it kind of simplifies the problem. And if I take the limit, right, as, in the limit as delta t goes to 0 of delta p over delta t, what I actually have is that average force F is equal to dp dt. But that's not the only way to get to this. I could have gotten to it from Newton's second law, because didn't I tell you that that's what Newton's second law is, the second form of it, right? Is the force in general, external force, equals the time rate of change in momentum of the system. So I could have started from Newton's second law and derived back this way. But whatever, I just wanted to show you that it all comes full circle. So now I can either, unpack Newton's law, or just take this and multiply through by dt again, and I'm back to this equation, but the differential form. And I have that the change in momentum, dp, is equal to um, the integral of average force F, well, is equal to F times dt. But then if I integrate, basically I get that delta P, the change in momentum, is equal to the integral of the average force, which is usually constant over the integral, times dt from T1 to, T final. And then, so that's one version. Actually, this is basically just the differential version of this guy. But then I can combine equations 1 and 2 and get a final equation for impulse, which is that the impulse J is equal to the integral of the average force over the time rate of change of the where the force is. And this is one of the equations you'll see that defines the concept of impulse. In fact, you might actually see 3 equal signs there. Definition. Yeah. So impulse is defined as change in momentum because of the graphical nature of the relationship between change in momentum and average force. We have this guy, and then we can put those two things together, and we get this guy. So these are equations that kind of define momentum or change in momentum or impulse. And again, the delta t is assumed to be extremely small. How small? Well, usually the amount of time it takes for something, a ball to collide with an object, which is usually somewhere between, something usually less than 2/10 of a second, three tenths, or between 3/10 of a second and smaller. Yeah, I mean, the best application for this is collisions. What I will do, since I talked about this problem quite a bit, I can just, we can do something like give an estimate of, show you how the value of these impulse relationships. So again, this thing is a pretty difficult thing to figure out. Like, what is the force? And when I throw a ball against a wall, approximate the average force of the ball on the wall. I mean, if you had to go Newton's laws route, it would be practically impossible. Well, not impossible, very difficult. You still probably wouldn't get it. For all that work, it would still be basically an approximation. So why not approximate in the first place and get an answer that's close, and you got much less work? So how do you do that? Well, understanding these relationships, there's certain external things you can measure. Like I could know the speed of the ball when it's going toward the wall, and I can certainly measure the speed of the ball when it bounces back. I could just estimate that here. I'm throwing a ball. Me walking across the room at a normal gait is probably 1.5 to 3 meters per second. This ball is probably, if I just throw it like that, it's probably twice that speed. At the most 3 times that speed, but maybe more like twice that speed. Let's say 3 times. So if I'm 1.5 meters per second, 3.3 times 1.5 is that 4.5? Is it? No, it's 4. Calculator. 3 times 0.5 should be 1.5, and plus 3 is 4.5. Yeah. So, and if we assume, that in the ideal case that it bounces back with the same velocity that it hit, then we could certainly calculate the average, the change in momentum, right? So the change in momentum would be so let's like um, yeah. So the problem consider like this: a uh, a rubber ball, a rubber ball is incident on a wall at 4.5 meters per second. Actually, let's make it even more interesting. Let's say it does give up some energy. So, and bounces off, bounces off at say 4.0 meters per second. You know, oh, so let's approximate. I don't know. Let's give it, be generous. 0.2 seconds. I think it's probably larger time, less than that. But let's say 0.3 seconds. Let's say the time of impulse, the time of impact is let's say 0.25 seconds. So well, approximately 3. So the collision is delta t equals, I don't know what's going on with these markers. It won't stay filled. Time of impact is t is equal to, let's say, 0.20 seconds. Let's make it that. So figure out the and oftentimes with problems like this, they won't tell you the time. They'll have you estimate it. So don't let that throw you off, making you feel like you don't have enough information. With certain common kinds of things, collisions or common things that you might be able to gauge an average time for that. That's what they're implying they want you to do, but not giving you a time of collision if that doesn't happen. Um, so yeah, so basically figure out the average value of the force on the impact force. So determine, or impulse force. So determine the the average force of the wall on the ball during during the collision. So here I'm not really walking you through the problem. You have to actually figure out the impulse first. I usually go for the jugular, right? You can see it's a short period of time, so it might give you an idea that it's an impulse problem. So you might start directly with that equation, with that the impulse, because that's where the average force is directly in that, is equal to this guy. Now, this is average inspector. So you take the absolute value. Well, you take the absolute value. Yeah. All right, so you know the delta t, right? If this force is constant, basically it comes out of the integral. So we're really talking about F average delta t. So in this quiz, you got two unknowns, right? The average thing you're looking for in the impulse. But the impulse, is related to, is defined as change in momentum. So J is equal to delta P. Substitute those, and here you got it. You got an equation that can give you what you want, right? That delta P, delta P is equal to F average times delta T. So the only unknown in that equation really is going to be this guy. Oh, I didn't give the mass of the ball. That's an unknown as well. So I need to do that. And let's say the mass is equal to 300 grams. I think I measured that before. So yeah, so we'll say M is equal to 300.0 grams. Yeah, so yeah, so we're done, pretty much, it's just a matter of doing. The physics is done, it's just a math now. Because delta P is final minus initial, right? So we're gonna have um final momentum minus the initial momentum equals F average delta T. Now, I don't know, maybe I could establish my coordinate system like so that that's the positive x direction. And of course, the positive y direction straight up. So the final momentum is, and I guess maybe we could take the absolute because it's going to turn out to be negative, isn't it? Final minus, yeah, the final momentum is in the negative direction, and the initial momentum is in the positive direction. So the change actually would be negative because of the way I set up the coordinate system. I don't know, I could turn it around. So we could just do it like this. So we could make that positive x and up y. So I'm looking at it from the other point of view. And So final is in the positive direction, minus initial in the negative direction. So that would be basically in mass times V, and V initial is V final minus mass times V initial equals average force delta T, which is mass times V final minus V initial equals average force times delta T. And so this is going to be sorry, I almost made a mistake. It's minus, but then the velocity itself was minus. The exact issue I told you to watch out for, and I did it. V final minus quantity minus, because this is a vector quantity, so you have to take that into consideration. Equals average. And just divide by delta T. So that's going to give it to you. Um, that's the same as V final plus. So, yeah, I just box that in. So that's the solution. And if we put in our numbers, 300 grams, that's 0.300 kilograms times the final is 4, so final 4.0 meters per second plus, because minus and a minus, plus 4.5 meters per second divided by 0.2 seconds equals the average force. So we'll see, it's probably going to be a pretty high value. I think these numbers are realistic, so it gives you an idea. So we're talking 9.4 or 8.5, sorry, 8.5 times 0.3 divided by 0.2. 12.75 newtons force. Okay, go with that. Average force. 12.8. Actually rounded to two significant digits because that's what I had. It was approximately 13. Approximately 13 newtons of force on this guy. Yeah. Approximately 13. All right, so that's an example of a collision deal, of a impulse problem. All right. Now I want to go ahead and introduce collision stuff right now. We can get that done. That'll be pretty much finished up the bulk of this chapter. For one and two dimensional collision. Knock that out. Mhm. Mhm. I changed up my ink here. Okay. All right. All right. Okay, what we got here? Oh, collision. All right. One-dimensional collisions. I've already talked a little bit about early on about the whole thing with I'd set up some kind of problems. I thought mental demonstrations with cars on air tracks. So let's revisit a scenario like that, or billiard balls, if you can imagine them on a tabletop. But I like the air track example. The billiard ball is it's an approximation. But the air track is really one of those situations where a simple design and experiment actually mimics the real thing, with no need for approximation. Well, no need for relaxing certain criteria. It truly is a frictionless situation, particularly when you have magnets on the bumper card. Now, there's two basic kind of overall, well, the two conservation theorems are going to be applicable in a certain way regarding collision problems. And the two conservation, we've really done, the two conservation theorems I'm referring to, those that we've talked about thus far, conservation of linear momentum and conservation of mechanical energy. Put this chart up in this fashion because it's a really nice way not to forget the criteria that you must apply to collisions um, to know how and when to use the conservation theorems in the application of collision problems. And that chart's going to look something like this, very basic, but very crucial. Because if you don't get this right, there's nothing in the conservation theorems that tells you you're wrong. I think I talked about it a little bit when I introduced work a while back, but you could end up using them, but not knowing that because you violated the criteria under which they should be used, that you're making mistakes. Nothing will tell you that. You have to know. So this chart should help you. It's designed to help you remember and know. So inelastic versus elastic collision. This is the terminology that is used. And for me, it's somewhat counterintuitive. I would always mix it up. So one of the things that I learned to do is inelastic versus elastic. And this column represents the theorem, the theorem. So the conservation theorem. So momentum versus energy. Oops. Okay. Momentum. Actually, you know what? I'm just going to use the symbol. So delta P is equal to 0, meaning it's conserved, or delta E is a different color. And I'll pick out your eye a little bit. Delta E equals 0. Now, before I can write down what's what, here's a very nice way to remember. As we've talked about before, when things collide, when they're in physical contact, technically there will be some kind of friction. Otherwise, you wouldn't be able, even if I'm just holding this, not rubbing it, just holding it. What's allowing me to hold it? Friction. Now, you might say, well, you're not, in order to do work, it's got to be like moving through a distance. That's true. But that's mechanical. That's on a simplified level, right? It's like, um, even on a quantum scale, right? There's interactions going on where energy is being transferred in some way. And so whenever energy is transferred, there is some work that's done. Period. Change in work energy means something is particularly, it means, it's another way to count whether or not there's been some sort of energy transfer. And so my point is that if that's the case, then generally speaking, energy is not conserved. If you have to touch something in some way, there's going to be some conversion of mechanical energy to heat. And even on a microscopic level. Now, you might say it's negligible, but whatever. So, inelastic, with inelastic collisions, objects touch. Inelastic meaning like when something bounces off, it's elastic. So the less it bounces, the less elastic it is. If it's inelastic or completely inelastic, it doesn't bounce at all. It hits and it sticks. Right. So yeah. Um, so that's the quickest thing to kind of identify between these two different types of collisions. Inelastic means that something touches between the two objects, and elastic means there is no touching. That's my very easy and straightforward way of approaching those definitions in a way that's practical and that I can remember them. Inelastic, touching; elastic, no touching. That above here. And so, anytime there's touching, energy won't be conserved. That's out. So only when there's no touching and there's no opportunity for conservative for forces to convert work to energy, convert heat to convert mechanical energy to work, then you will have a conservation of mechanical energy with regard to that system. So we can check that off. For inelastic and elastic collisions, it's really about momentum, as we've seen. Momentum is, well, we'll just say that. What is the criteria? And so in this case, you can see that the criteria is not satisfied here, but satisfied here. The criteria that energy is conserved. What's the criteria? Only conservative forces do work on the system. So if only conservative forces doing work on the system, as I told you early on, a quick and dirty way to identify a conservative force is that it doesn't have to touch the object in order to do work. So gravity, magnetic force, electrostatic force. In an ideal case, a ideal spring, which is massless, number one, and only touches it at a point where the area is very small. So even if it's massless, though, there's not going to be, mass is a normal force. Friction is a normal force times a coefficient of friction, but the normal force is going to be associated with the mass. So if it's massless, again, simplified case. Criteria that momentum is conserved is that the net external force on the system is zero, external force. So when two balls are colliding, as I set this up earlier, both of those are part of the system, and they do have forces on one another, but those forces cancel out, they're equal and opposite because of the third law. But even if they didn't cancel out, they're not external forces. So it has to be external forces that's equal to zero. And in that case, they still would be. So in both inelastic, obviously when things don't touch, that's the case. But even when they do touch, for inelastic, and during a collision, you still have the net external force of the system being zero. So in both cases, momentum is always conserved, inelastic and elastic, but only in the case of elastic is energy conserved because there is no touching of the object in order to apply the conservative force. All right. Any questions about that? Good. Oof. Sorry, I need to take another like 5 minute break for a second here. Right back. Oh, just thank you. Thanks. Forgot to take that off. Thank you for that. Yeah, so I was saying we're going to look at collisions, inelastic and elastic. I'm going to do inelastic right now, and it's a situation where, let's say we have bumper cars or air track cars. One is completely stationary, the other is moving along at a constant speed. They collide and then they move off together. So it might look more like this. Come along, bam. Inelastic is when they don't collide. They collide, but without touching. You might say, well, how does that happen? Well, if you put magnets on the cars, they would bump into one another, and without actually touching. And you could see that it's beautiful. You get a lot less error, minimal error and everything because there's no friction. Anyway, the first one, inelastic. They hit and connect completely and move off together. So yeah, so we'll set up a scenario. Both cars could be moving under circumstances, but I'm going to set up a simpler scenario where, as the one I just mentioned, where one car two, for example, is not moving. So its initial velocity V2I is 0, and V1I is non-zero. It's moving along, to the right. So they're going to hit, right? When they hit, they couple. And then move off together with one final velocity. So this is M1, M2, still M1 and M2. Okay. So in all of these, we're going to assume that the initial velocity is known, and we're going to derive an equation for the final velocities and all these problems. And this problem is just one final velocity. Now, right off the bat, you might be tempted to apply conservation of energy. As I said, the conservation theorems are, more elegant in that they usually you can do pretty sophisticated stuff with less mathematical rigor, uh, and that's usually how you pack more into less, which is usually generally the definition of elegance in a mathematical equation. But the problem is, well, it's not a problem, but the trade-off is that you lose what you gain in power, you lose in transparency. Elegant equations are a little bit more take a bit more sophistication to be able to manipulate and use appropriately. Yeah, that's it's just that simple. So that is the case here. That if you were to start off using this conservation of energy with this problem, there's nothing in the physics that's going to tell you it's inappropriate. There's no checks. Yeah, the only check is that you know the criteria under which you should use it, which is that you can only use it whenever there's no mechanical energy to convert to heat. And that will always be the case if objects are touching. So in this particular case, you would have to know from the very beginning that only conservation of momentum applies, not conservation of energy. So we'll do that here momentarily and we'll get a solution very quickly. Now, here's one of my major pet peeves in mechanics at this level. Having said what I just told you, I can assure you, you can take this to the bank. What I just said is absolutely true. There's no exceptions. unless you make an exception and specifically state that, which is usually done in the case of billiard balls, which is why I don't like to use that as an example of, of the first collisions. But some people do, and many books do. Fine for an example. I don't like to use it as a first example. I do it, but not as a first example. And this is why. Because that's usually in most books a situation where they use to show, they call it an elastic collision, meaning both energy and momentum are conserved. Now that violates what I just told you, but it's usually done and accepted because it's a special case, right? It's a case where you're assuming that even though they touch, because billiard balls are solid, because they don't really deform much, as the whole conversation I was telling you at the beginning of this class, which is why you lose energy, the deformation, basically, that you're doing, the wall is doing work on the ball as it squeezes. Actually, that's a pretty good problem to try to approximate how much work does. Anyway, but it's a little complicated because those things are not, they're not constant, as we said before. But anyway, oh, that yawn made me forget what I was saying. I'm so tired. There is nothing in the conservation of energy theorem formula that will tell you you're using it appropriately, specific to the criteria of its use. So you just have to know. That was something really interesting I was going to say too. It just left me. Why? Just so tired. I think it's gone. I don't think it's coming back. Really juicy. Well, you do have to know, and in this case, we are using it appropriately, so we can use conservation of momentum and apply it to this scenario to solve for the final velocity in terms of the initial velocities of the system. And so without further ado, that's what I'll do right now. Yeah, billiard balls. I'll get back to that in a minute. Let's go ahead and do this. So I like my favorite form of these conservation theorems. We can say a momentum initial equals momentum final. It's a vector. I'm going to emphasize that, placing the vector quantities. Now it breaks down. The system has two particles. So here I have the initial particle 1 times its initial velocity plus particle 2 times its initial velocity. Now, if this velocity were non-zero, then I would definitely have to. I mean, there's a couple ways you can handle this. You can put in the vector signs, in which is always would be plus, where we define that here, or when you relax the vector signs, you put in the actual signs appropriate to the specific direction. So if I did that here, it's still just positive because the velocity of the second car is 0. So M1, E1 plus M2, V2 initial. And that equals M1, V1 final plus M2 V2 final. And in this case, as I said, this term initially here, this term is 0. That's 0. Now relax they're both moving in the positive direction if you call right positive. You set up the axis like that. That's going to be M1V1 final plus M2V2. Well, actually, here's the thing. Be careful about this. When they're coupled, there's no V1 final and V2 final. There's just one final velocity. So really, I could start off by writing this term like this. These are coupled. So the total mass is M1 plus M2. And whatever final velocity that is, that's what it is. And so now you can see what's nice is when I come to this next step, I'm pretty much done. I'll just write this down again, M1 plus M2 V final, and I don't have to put a subscript there because they're both coupled together. And over here then, I get that basically V final over there, this is a mass, so this is going to be V final, it's going to be equal to V1, velocity of the first ball, a first object, divided by, or actually multiplied by M1 times this whole ratio of M1, M2, the total inertia of the system. Yeah. So that's it. That gives me the final velocity of that thing. And for an initial. And you can see what's nice. We'll go through this a little bit more at the end when we get everything derived. But what you can see is that the final velocity of both cards coupled together is slower than the initial velocity of the first card. Because I'm dividing, so this numerator, this is less than 1. It's a number between 0 and 1. But less than 1. And so I'm dividing my initial velocity of my first car by something less than 1. So the final velocity is definitely going to be less than the initial velocity of car 1. In fact, it is. You could do a really nice experiment if you say that the cars all have the same mass. What if M1 equals M2? Just equals M. Well, what I have is V final equals V initial over M plus 2M. And it's cancel out within times. Yeah. Oh, yeah. So basically, I have that in that special case where M1 equals M2, the final velocity of the coupled thing is going to be equal to V1 over 2. How about that? So the velocity cuts in half. I mean, you probably have seen, again, the air track is really just awesome in demonstrating these things, but you could probably find it on YouTube someplace. I could probably find it for you, but I want to get this finished, so I'll let you look that up afterwards. But if you Google inelastic elastic collisions on YouTube, you'll see several demonstrations of these. So that's it. Sorry about that. Checking something out here. 10 minutes left. So I set this up for an elastic collision. As I told you, for an elastic collision, both energy and momentum are conserved as per that chart. And again, let's do the scenario where the second car is initially at rest. So they come along, they bounce, and then what happens, to the cars afterwards? I guess I should establish, actually, turns out what I just did establishes that M1 is greater than M2. But we'll see all the different possibilities once we get everything derived out. Probably won't be until on Wednesday, but I'll start it. And you can read through the derivation in your book. And again, different books you're going to see, there's different versions of this. I could have M2 moving in the opposite direction. Obviously, its velocity, its speed would have to be less than M1, otherwise they would never catch. But it could be moving along like that and then I catch up and hit. Or it could be moving in the opposite direction and hit. So there's three different scenarios that, and they're arbitrary, and you pick up one book, they might do what I'm doing. The next book might make, the car two move away. The next book might make car two move toward car one. In the end, once you kind of look at all those different solutions, usually what's done is the generalized solution is given at the end, putting in plus and minus signs for all those possibilities. So just keep that in mind when you start reading through the section there. So what am I doing? Yeah, so you start, applying whichever one you want, whichever conservation theorem you want. This is elastic now, so they're not touching as they bounce off. So I'm going to erase this thing here. It represents a magnet or something, but just do the result. So since we applied momentum first, and since nothing is touching here for an elastic collision, let's go ahead and apply energy first here. So elastic collision. Maybe my circadian rhythm is off, but I was supposed to got like an extra hour of sleep today. Yesterday, but I'm reading. All right, so energy. So how do you apply conservation? So let's back up over here. Let's just back up again and do it all over. I mean, I've done that, right? Oh, I'm not going to need that. Yeah. So this is elastic collision. So elastic. So energy one, E1 equals E2. If I'm not on an embankment and I have any other potential energy functions associated with this, like there's no magnets or electric, the cars aren't charged, so that there's other conservative forces acting. In this case, then the total mechanical energy is kinetic, because potential energy, I could just say that the ground has zero, and so zero potential energy would be zero at that point. So other things that we could do, but that's what I would do here. So in that case, we just have energy, which is just, as I said, all kinetic. So 1/2 mv1 squared, and you have to put initial or final. Basically, plus zero equals 1/2 mv1 final squared plus 1/2 mv2 final squared. Immediately, you see that the 1/2s go out. And I forgot to put the subscripts on the end. M1, M1, M2. Yeah. I'm going to get all the one stuff, like block one stuff on the same side versus block two. So I'm going to take over this M1 and V1 squared. Remember the halves are gone. So this is going to be M1 V1 initial minus M1 V1 final, and those are both squared. And that equals this last term that's left here, M2 V2 final. In fact, M2 V2 final. Okay. 1, 2, 3. Yeah, so here's a deal where I'm going to use a mathematical aside over here. Basically, the overview that you've got two constants. I guess I didn't really say that with the chart that I made, but it's because I'm saying it now, I guess. But you know how you always need to set up to determine and create a system of equations that you're going to use some method to solve in physics. And we've been doing that with Newton's laws and kinematics. So I've been teaching you. And even now we add in things like the force laws and stuff and graphical implications. There's a couple ways where we can get relationships and translate those into quantitative equations that represent, the physical quantities that are defining these phenomena. That said, I lost my train of thought again. What's going on with me today? Yeah, I don't even know what I was saying. I don't know how that left. I'm like getting sick. I'm just tired. Well, let me just go ahead and knock this out. So with this derivation, oh yeah, it's talking about uncoupling the equation. So you always want to have the same number of equations as unknowns, and I've made that implicit in the problem solving technique that I've taught you. But here, the collision problems are already set up for that, meaning the two equations are always going to be conservation of energy and conservation of momentum. And so those are the two equations that we are trying to apply to any system and then solve simultaneously. The problem, though, and one reason I like to do this in class is because in the energy equation, because you're dealing with kinetic energy, the velocity, the speed is coupled in the square term. So if I were to try to use that with any of the momentum terms prior to manipulating it, it would be a disaster. So what I'm doing right now is I'm deriving the um, I'm have to uncouple the square velocity term in the energy equation so that when I get conservation of momentum, I'll have something simpler that I can solve simultaneously. And right now, the square terms, if I try to substitute into that or solve it and substitute, if I substitute into it, I'm going to get things blowing up into squares, a bunch of terms. If I take the square root and substitute that in there, and I haven't put the conservation of momentum equation down yet, but I will get it, then I'm going to have radicals in it. So I got to decouple it. One way I can do that is using this algebraic, that's the product, the difference of squares, right? If you have a term, remember that you have A minus B quantity squared, that's the same thing as A minus B times A plus B, right? Well, here, if I look at equation 3, I can turn this around, right? And I'm going to go ahead and finish this little part. We get this done. And I'll start here on Wednesday. It's a good start. Not the best starting place, but it's a good one. So Yeah, sure, I'll call this equation 4. If I factor out M1 from both of these terms, I'm going to have, actually, that's not, is that what I want? No, it's the difference of squares. Sorry, that's not it. It's this guy, what I'm talking about. That guy is equal to that thing. So here I have V1I squared minus V1F squared. V1F quantity squared equals M2 V2F squared. So over here, I'm going to have M1 times V1I minus V1F times V1I plus V1F equals M2 V2F squared. Yeah. Well, what time is it? Yeah, it's right at 4:30. Well, now I have to get conservation of momentum. You know what? I think that's a good stopping point. I'm going to let that because this actually is a long, kind of a longer derivation. There's a lot of stuff, moving parts in here. It's algebra. It's not difficult. It's just long, and there's things I want to say along the way. But that's a good stopping point that I'm on the verge. Because the next thing that I do is then apply conservation of momentum. So momentum final equals momentum initial. So I'm gonna stop there. You can finish the derivation. You can start there, maybe read the book, see if you can apply conservation of momentum, then get a relationship there that is a relationship of initial and final velocities of both cars. And the trick then is that equation that you get, that result, you divide that into this equation and it decouples so that you can use that result and conservation of momentum, the same one, so that result and conservation of momentum again in order to solve for the equations for the velocities of each car in terms of the initial velocities, the final velocities of cars in terms of the initial. Um, yeah, yeah. Yeah, so I'll kind of review that again really quickly when we do on Wednesday, but I'm going to let you go. I'm not going to, because this will take probably another 20, 30 minutes for me to do it in the way that I want to do it. And I don't need to do that now. We're not behind, and you can read up a little bit between now and then. So I'll go ahead and dismiss class. I will get to you still there. I will take care of that stuff before the next class. I'll take a look at it probably tonight. But I'll get to you. Thank you for reminding me. Yeah. So if you don't have any questions or anything, I'll go ahead and dismiss class.